Okay, so for my video, I'm going to go over how to find the moment of inertia of a composite body about a point P. So we're going to go over this problem here. So in this problem, we have a rigid body consisting of 4 smaller bodies joined together. Those 4 bodies are this disk, this rod, this rectangle, and then a point mass at P. So, first of all, what is moment of inertia? So moment of inertia is basically the rotational analog of mass. So it tells you how much torque you're going to need to get a certain angular acceleration of a body about a specific point. And so when you have this type of rigid body with different bodies of certain shapes joined together, you can use the fact that the total moment of inertia about a point is going to be the moment of inertia of each body about that point added together. So we'll show this. Here we have some code. We have some code for this problem. So what we did here in this code is we took our givens, which we have already, and we found the moment of inertia of each body here about point P and just added them together. And then that'll give us the total moment. Now, how do we get each moment of inertia about point P? So we start with the disk. How do we get the disk's moment of inertia about point P? Well, to do this, we can start by finding the moment of inertia of the disk about its center of mass. And we have an equation for that given here. And that's this equation here, 1/2 mr squared. Simple enough. You can derive that, but we were given it. So I'm just going to use it. And so the main point is that now we have the moment of inertia about its center of mass, but we don't have it about point P. So this is where you want to invoke parallel axis theorem, which says that you have the moment of inertia of a body about a point, and you're trying to find the moment of inertia of the same body about a different point. You can take the moment of inertia of that body about the first point, which in this case is the center of mass, and then add to that the mass of the body times the distance from the first point to the second point squared. And that'll get you the new moment of inertia about a different point, which in this case is P. So here we have the moment of inertia about the center of mass. We added to it the mass times the distance between the 2 points squared, and that gives us the moment of the disk about point P. Next up we have the rod, and for the rod we actually have a specific equation that gives us the moment of inertia about a point at its end. So we don't need to use the parallel axis theorem. We can just directly apply this equation, and that'll be at around point P. So that equation is 1/3 times its mass times its length squared. And then for the rectangle, we have an equation that gives us the moment of inertia about its center, 1/12 m times width squared plus height squared. Then we use parallel axis theorem for that as well. In this case, it's its mass times. This is a little different. So this is a vector from the center of mass here to point P. So that's going to be, and for the x component, it's going to be the width over 2 plus the length of the rod to get us to the x coordinate we need. And then for the vertical coordinate component, we're going to have R1 of the radius of the disk. So we have this vector like that. So now we have a vector that goes from here to here. And norm is just going to take the magnitude of that vector. So it's just going to be the length, so the distance squared. square it because that's what you need to do for parallel axis theorem. And so that's the moment of inertia of the square about P. So finally, like I said before, you can add the three together to get the total moment of inertia. We don't have to take into account the point mass at P because there's no distance between the point mass and P. So therefore, there will be no moment of inertia from P, from the point mass around P. And so finally, we run the code. So you get 70.83, and see, got that. That's the correct answer. So that's how you find the moment of inertia of a composite rigid body about a point.